In our latest tutorial, we show how MLatom can be used to simulate UV spectra via single-point convolution and nuclear-ensemble approach. Machine learning can also be used to increase precision of the nuclear-ensemble approach spectra at reduced cost. So here we also demonstrate on an example of a benzene molecule how to calculate its UV spectrum by single-point convolution. And that's the easiest type of calculations and the simplest one, so it might be not the most accurate one, but gives you very quickly an idea about the electronic structure of a molecule. So first of all, we do geometry optimizations with a chosen method, which can be different from the method used for calculating excited state properties. And then we can predict for this geometry excited state properties using a method of choice. And in the tutorial, you can find information which methods are supported. Then you can choose number of electronic states for which you calculate. And then after calculations finished, you can dump the file with all the information into the JSON file for later use. You can also print some information from these excited state calculations, like oscillator strengths and excitation energies. Then you can plot the spectrum with this very quick plotting command. So here is a function of extinction coefficients of as a function of wavelengths, and you can dump the spectrum too in some digital format. Now you might want to also play with the broadening, so then we provide some a bit more elaborate routines. So here you can choose different broadening factors and see how your spectrum changes. If you have an experimental spectrum, you can load it, and then you can compare to the theoretical spectrum. And here it might be useful to perform the broadening of the spectrum to much closer with experiment. Of course, it is a bit arbitrary how to do it. That's why there are better approaches like machine learning accelerated nuclear ensemble approach. But it gives you a pretty good agreement with experiment. Here we also shift theoretical, like make a shift to the theoretical spectrum to much better. So that should be printed and mentioned if you put it in your publications. Here we demonstrate on an example of a benzene molecule how to calculate its UV spectrum via nuclear ensemble approach. First, we load the initial gas for geometry and define our electronic structure method, can be also machine learning one. And then we optimize the geometry in the ground state, can be with a different method than the one for excited state calculations. And we can do frequency calculations to obtain later with it nuclear ensemble. First of all, need to mention that there are several ways to obtain ensemble of geometries. One of them is through Wigner sampling. Another one is through molecular dynamic simulations, which you can also do with MLatom. Now we show here for simplicity Wigner sampling, so which just requires the frequency calculations, and then you can perform visualization of normal modes. You can also do predictions for this optimized geometry, but we need to calculate electronic structure information for many excited states and also for many nuclear configurations. So in this case, we obtain our ensemble of nuclear configurations by using Wigner sampling via this very simple command. And after we obtained our 100 geometries here, we can perform electronic structure calculations for all of them in one go, here for 30 electronic states. And after all these properties are calculated, we want to save the database with all the calculations for later use. And we can also finally obtain the spectrum by using nuclear-ensemble approach, by providing ensemble as input as a molecular database and choosing some broadening widths. So then you can recalculate very fast with different broadening widths as you wish, and then you can make a quick plot to see how it looks like. So here, and later it might be useful for you to compare with experimental spectra, and it may be done with this plotting routine, where we also compare to the single point convolution spectrum. Finally, machine learning nuclear-ensemble approach provides you the highest precision of the calculations because it accelerates the simulations for different nuclear configurations, so you don't need that many electronic structure calculations as without machine learning. So here we provide for now just a solution via input files, and the nice feature about it is that it automatically determines the optimum number of training points, and then it stops generating electronic structure reference data. Here after just 4 iterations and 200 training points, which is quite good. Also, if you compare to experimental data, so the shape is more or less okay, although it's all shifted, but compared to the quantum chemical calculations, the precision is even higher. So you can find more about this in the manuals, for example, how to do such calculations from scratch. In the future, we'll implement also easier way to do it with Python API.